Right, this week I've got something special for you. Signal detection theory. It's not in the textbook, if you checked on that, because it's a bit outside the scope of the basic textbook. But it is absolutely necessary to understand the basics of that, to understand any kind of experiment that we're doing, because that should give you the background of how we measure something subjective. You must realize, you have realized last week already, everything that we measure in sound perception is subjective, and signal detection theory gives us the tools to make this objective measures. Okay, what are the learning outcomes? And this week we are going to understand the basic ingredients of any psychophysical experiments. We're going to understand how to perform and analyze simple psychophysical experiments. They're actually not that simple, they're actually quite complex. And we're doing a practical in which you will measure your own frequency discrimination threshold. I've got a worksheet here for you. You do your own little experiment. This is an actual, real psychophysical experiment, so you need two people. And I want you to do that, to perform it, and to describe it, and to understand it, obviously. It's not trivial. Okay. What are the ingredients of a standard signal processing experiment or sound perception experiment? We've obviously got a sound, or what we sometimes call a signal. If I use these words interchangeably, usually the difference between a signal and the noise is that noise is a sound as well, but we have usually a signal that we want to detect and a signal that we don't want to detect, namely everything else, and that's what we call the noise. We have the perception, that's what we're interested to measure, and we need some response of the subject that we interpret. Okay, let's make a little black box experiment. The subject is our black box, everything happens inside the subject. In goes the sound from a loudspeaker or a headphone, that's a beep usually, and the subject clicks a button, a change in behavior. So that's what we observe. They say, well, what we did so far, we say yes or no. In slightly more professional experiments, you've got a button that you press. You might have done that yourself in some experiments where you measure hearing threshold or something. But the end effect is the same. You get a result which is either a yes or a no, usually, which is perfect for a button because you can either press it or not. But what happens in between? That's the perception. And we have a little model for that. We say we have an auditory system. That's what we started to talk about last week ago. With the ear, middle ear, outer ear, inner ear, and all that sort of stuff. That is physics. That somehow translates the physical sound waves into something in our brain. But we also have a decision maker in the brain that tells us, yes, now it's time to press the button or not. And after you've done the threshold experiment, I hope everybody had a feeling for that there is a lot of subjective effect on that. It's not only that there is a lot of noise in this room, which makes it sometimes difficult to hear or not, but the pure decision, do I hear it or not, is not as easy as it seems. Because it depends on a number of factors. Specifically, it depends on your setup or your motivation to do the experiment. Okay, let's do this slightly more formal way. I define here what I call the standard experiment. That's pretty much what we did last week. I call that a yes-no paradigm. And I think I can't play these sounds to you. Let's try what happens if I click on that. Nothing. They are on Blackboard. It's what I uploaded. Okay, what's uploaded as example series of SNR. But if you don't listen to it, don't worry. It's basically what we did last week. You have a signal, that's a pure tone, and we have a noise. In this case, I add specifically noise to the signal. Why do I do that? Because I at least can control the noise. In this environment, I can't control the noise. But very often we are interested in how good are we in detecting a signal in noise. That's a very crucial question. And so what I do is I just generate some noise, pink noise in that case, and I put a signal in and I let the amplitude of the signal go down. And that means I increase the signal-to-noise ratio. The signal-to-noise ratio is just the relationship between the amplitude of the signal and the amplitude of the noise. Okay, so the goal of this experiment is to measure the threshold of perception. If we don't add noise, we measure the absolute threshold of detection. If we have noise, we have a relative measure, because then we know how much SNR we actually need, how much the signal needs to have energy in comparisons to the noise, which is a little bit more powerful concept, of course. Right, so you would listen to the sound and background noise, and you're asked if the sound is there or not. So what we do is basically count 1, 2, 3, 4, 5. But that's the same as if I would ask you for each individual one, do you hear it or not? And that's the basic setup of that. But that's what we call the yes or no paradigm. Each of these tones you either hear or you don't hear. Okay, your response, this is all very similar to the threshold experiment, only in this case we add noise deliberately. The disadvantage of that is that our subject can cheat easily, because you can just say, okay, I heard 7 sounds, although I only really heard 6 sounds. That's clearly a disadvantage, because we want to get rid of exactly that problem. The advantage of it is, if you can read it, it's very fast, because you will not find any experiment to measure a threshold as fast as in this way. That's why I did it, because it's really, really, really quick. And because this is so fast, it is actually the method of choice in any audiological clinic. If you go and have your ears measured, if you have a problem and you do an audiological professional experiment, what they do is they do pretty much exactly that. They don't ask you to count the sounds, they ask you, do you hear it or not? And then they go down in amplitude until you're not hearing. So they rely on you to say yes or no. In fact, they rely on you pressing a button, but that's the same thing. Okay, the reason for that is because it's so fast, but it has a disadvantage, and this is what it's all about, because it includes the subjectivity of the subject, the subjectivity of the perception. And what this lecture is about is how can we get rid of this subjectivity. Okay, let's give an overview. We have a signal and a noise. It's called SNR. I'm sure you've heard that abbreviation. That is objective, but the response to that is subjective. So both are connected by a psychometric function that I'll show to you in a few slides. But in order to understand this, we need the concept of probability density functions, which some of you might have heard already, called PDFs, but let's explain to you what they are anyway. Probability density functions is a description, is a graph, most of all, that shows the probability as a function of any variable. So we put any variable x on here, and we've got this usually characteristic bell shape that gives us a probability. So we put on the y-axis the probability. So that means if we measure the probability of any event, then in this case x equals 0, the probability would be highest. We get at x equals 3, we would get a very low probability of something happening. The point is, the area under this curve is always normalized to 1. Okay, why is that useful? It's a very useful concept in nature in general, and statistics. Once you do some more powerful experiments in statistics, you'll learn a lot about these. These are called normal distributions. I show you some examples from probability density functions from nature, well, or something like nature. I just popped that from Google just to show you how these distribution functions are everywhere. Basically, if you put a histogram and you put a distribution over it, that is a probability density function. But this is to show to you that most of these probability density functions in nature are in fact of a typical shape, namely of a normal shape, that's called normal, or Gaussian shape. So this, for example, is the weight of a pound coin, which is randomly distributed. It's not always exactly the same. It's about 7.5 gram, but it can be a little bit less, a little bit more. But the point is, it is actually distributed. So you know, if you have this distribution, you can predict how many of pound coins are exactly 7.6 gram. It's about don't know what this axis is, but it will be something like 5% of them. Okay? That's the relationship of radiotopes and soil, just completely random, just to show you that any physical measure that you do is distributed. There is no measure in nature that has always the same value because of the process of measurement. So there's a bit of variation. Daily temperature in January in Geneva, nicely normal distributed. That's the psychological example. That's the yield of a bond, will always be normally distributed. Or a digital camera, the light intensity, pixels, and a digital camera, you've got very many that have an average distribution, and then you've got a few pixels which are very black and a few pixels which are very white. That's how it works. Okay, so these are PDFs, probability density functions. What have they got to do with our psychophysical experiment? What we need to do there is to come to terms with what I call this decision axis. Let's say we do the experiment. I give you exactly one noise and a tone inside, and it's just about threshold. Okay? Or that's easier. We start even easier. Only give you the noise. Shh. Okay. Something in your brain responds to that and represents this noise in some random way. I don't know how it is happening, nobody knows really, but what we do know is that we can put that on an axis, which I call decision axis, which is proportional to maybe the energy of the representation, not the energy of the noise, the energy of the representation, maybe somewhere up here in my brain, or the number of spikes, neural spikes, on this part of the basilar membrane. It doesn't matter. Any measure that represents this noise will be distributed normally. So I've got a very high probability. The zero, don't take that serious. It doesn't really mean zero. It means this is the average of this distribution. Okay. If I only play that noise, something in your head will, if I play it 100 times, will be distributed like that. Fact. Well, that's not fact. That's our assumption, but it's a very good assumption. Now, if I present a signal which is quite a little bit louder than the noise, a little bit louder, so you hear it most of the times, then this internal representation is shifted to the right. You get more spikes or more energy because this signal actually does something in your brain that makes you detect it. And so on our decision axis, we will have a distribution which is slightly shifted to the right. So this is our distribution, noise only, and signal and noise. Okay? So we assume that the subject always chooses the interval with the larger response, and the problem is that these two overlap. So in any case, because in reality these go never down to zero, in any case, whatever we observe, so what we have on this axis is what we take our decision on. That's what happens in our head. Let's say there is a certain activity in the brain area, and that happens to be here. What do you do if you only have that knowledge? You don't know if you have only your noise or if you have the signal and noise. If you're over here, you're very sure that there is a signal. If you're over here, you're very sure there is only noise. But if you're in the middle, you have a little bit probability of both. And that's the whole point. We're talking about probabilities, and the one thing that we know about probabilities is that the area under these curves is always 1, and that gives us the possibility to calculate these in a little bit more detail. Okay, the measure that we use to say how much how much a signal is audible in noise is what we call DPrime. So this little line up there means prime. If you type in DPrime in Google, you get lots of results. If you type in D line, you don't get anything. That gives you a measure how different are these intervals. I call these intervals because one interval has only noise, or one sound has only the noise, and one sound has the signal and the noise. So how different are they? That's the definition, is that this difference between them, between the averages, is the difference in perception between the two. But you've got a variability in perception in each of them. And we assume that they are both the same, which is a good assumption. And if we divide the two by each other, the difference in perception divided by the variability in perception, you get a measure for the difference. If that measure, just as a rule of thumb, if that is 0, that's not a rule of thumb. If that is 0, it means these curves are the same. There is no difference. There's no way of telling these parts apart. There's no way of telling if there is a signal in the noise or not. As a rule of thumb, if that is 1, so if the variance is pretty much the same as the difference between them, so the way that I described here, that's about threshold. That's what we call a difference. You can hear the difference between the two. At the moment, this is only a rule of thumb. But what we want to do later is, of course, calculate this DPrime to tell us how big the difference really is. And obviously, the bigger the DPrime, the further these distributions are apart, the easier it is to hear the sound. Okay. Let's define these words. We talk about threshold of perception. That's the level at which a subject detects a signal on a fixed percentage of presentation. There is no general rule how much that is. That depends on what you want it to be. You can either go very high and be very sure, or you can go very low. If you're guessing, that's what we know. If you guess between two signals, you've got 50%. Yeah? That's obvious. So you want to be above 50% for threshold. To say your threshold is 50% doesn't make sense, because you get 50% by guessing. So quite often we take a value of around 75%, so you need to be correct in 3 out of 4 cases. And we call that's the threshold of detection. Right. The response form a probabilistic distribution due to this intrinsic variable. We said that. And we have this concept of an ideal observer that responds whenever the signal to noise exceeds a fixed criterion. So in our case, I hope you can see it from there, we've got our noise only and our signal and noise distribution. Our ideal observer would always have a criterion that it says anything below here, there's only noise, anything above there is signal. But obviously, it depends where we put our criterion. It can go further to the left and further to the right. Okay. The detectability, that's what we want to know. The detectability is a standardized measure of separation of the distribution, and that's what we call DPrime. And that's what we define. DPrime is the difference between these two distributions divided by the standard deviation. Right. Not going into detail here. What about this psychometric function now? That's what I said. That relates our perception, the subjective perception, with our objective measure. What we put in is on our decision axis, and we can put it here as an SNR, which we express in DPrime. So if we have a DPrime of 0, that's what I said, you can only guess. DPrime of 0 means the signal is so quiet that you can't hear it at all. You will be always have to guess if the signal is there or not. Then you have a 50% correct chance of saying you're correct or not, if the signal is there or not. If you go higher in DPrime, 1, 2, 3, 4, you get better and better, up to high DPrime values, 3 or 4, where you approach 100%. Okay. Now the threshold, obviously, is a theoretical process up here, and it happens that the DPrime, if you set that to 1, then you have a 76% chance of being right. That's where the 75% comes from. It's not exactly 75. We quite often use 76, which is equivalent of a DPrime of 1. So if our distributions are separated by just 1 standard deviation, then we have a reasonable chance, namely 3 out of 4 cases we get it right. Okay. Let's talk about some terminology of that. Probability, we're talking about probabilities. And we have the probability of x is, for example, the probability of condition x. For example, the probability that it is a sunny day. We have conditional probabilities, that you need to understand further more and more, because statistics becomes more and more about conditional probabilities. And let's say we have the probability that we have something else given. Namely, for example, the probability that it is a sunny day if it is August. So that's what we read, PA vertical line B. Why do we need that? Because we want to make a table now of possible outcomes of an experiment. Take that forward. We have a signal or a signal of noise together, and we either detect it or we detect it not. Let's write these probabilities. So either we have the signal or we don't have the signal. We call that N because it's a noise condition. That's the signal and noise condition. And in each case we have two different possibilities, namely the subject detects. So it presses the button or it says yes. That's what we call signal. And that's the probability is given by the probability that the subject says yes, given there is a signal and noise. The other one, the subject does not detect, so it says no, and that's the probability. And of course we have the other two opportunities. Signal is not there, the subject still says yes, or the subject says no. That's all four possibilities that we have in an experiment, all four outcomes. Okay. Why is that relevant? Let's go back to our probability density functions and say that our example have a subjective criterion. Namely, on this decision axis, the subject needs a certain activity in its brain to detect this signal. And he needs this much activity down here. It's not an ideal observer, so it's not over here, it's not in the middle, but it's slightly shifted to the right. So we've got the probabilities that I just said. So the probability of a signal given that a signal and noise. That's what we call a hit, or a true positive, or a correct detection. So there was a signal, and the subject said, yes, there was a signal. That's good. That's the probability outlined here. Carry on. Same subject, same decision criteria. This is the probability that the subject said, no, there isn't a signal, but in reality there was one. So you're on this distribution, but you're going to the left here. So it's smaller than the other one, luckily, but that's the miss. That's bad, because the subject obviously misses the actual effect, or the actual signal there. The other two are just symmetric. That's the probability that there is no signal, so the noise probability, and the subject says, no, there isn't one. That's what we call correct rejection. Okay, there isn't a sound, and you say, no, there isn't one. Last, but not least, is you don't play a sound, but the subject says, there is a sound. That's this bit down here. That's the probability of the subject says yes, but there isn't one. That's what's called false alarm or false positives. Okay, put them all into a contingency table. So this one here is us. We know that there is a stimulus, or there isn't one. And this is the response. That's what the subject says. Yes, there is one, or no, there isn't one. And we've got these four outcomes, namely hit or miss, if there is one. If there isn't one, either false alarm or correct rejections. What we're interested in is, of course, are the hits. Well, it depends what we're interested in. If we sum these two, or when we sum these two, we get 100%, because the number of hits plus the number of misses is always the number of experiments that we did. Equally, false alarms plus correct rejections is this number of experiments that we did. So we only need two of these values. Usually we decide we want to know the number of hits and the number of correct rejections, and we know everything that we need to know. And that gives us, together, we can calculate the DPrime, and we know everything about the experiment that we need to know. With the exception of one measure, namely the criterion, and this is where it all breaks down. Right, I said here, the subject has a subjective criterion over here. Now, an ideal observer would be in the middle, but you can shift it to the right and to the left. And there are ways to shift subjects from left to right very easily. What we did last week, I didn't say anything, so everybody might come up with their own criteria. The problem is, there are people that are more cautious, there are people that are more daring. And there is a very easy way to imagine how you can shift these. Imagine you would get £10 every time you're correct in your prediction, but you don't lose anything if you're not correct. What would you do? You would always say yes, because you haven't got anything to lose. That would shift your criterion over here. The other option is, you get an electric shock when you're wrong, but you don't get anything when you're right. You become very cautious of what you're saying. Probably always say no, there isn't anything, because you never want to get electric shock. You shift your criterion over here. So it is elemental what kind of criterion you take, and this is very, very hard to take into account or to prescribe, because we usually don't give subjects money or electric shocks. We actually want them to be in the middle. And that's why this experiment is fundamentally flawed. And we have no control, usually, over this, this criterion. We can put that into what's called a receiver operating characteristic, this criterion, by the way, which is very straightforward. We put on the y-axis the probability of a hit, and on the x-axis the probability of a false alarm. And what you want to be, you want to have 100% hits and no false alarm. You want to be up there. That's perfect. Perfect we don't do. We have always something which is slightly less perfect, and depending on how far how loud your signal actually is, the further to the left you go. If you have DPrime equals 0, you're just guessing. Then you have always the same number of hits than false alarms, because you're guessing. If there is actually a difference, DPrime equals 1, you want to have a high number of hits for a small number of false alarms. So the ideal is always to be on a diagonal in here. These values are also called sensitivity and specificity, or in fact 1 minus specificity. If you have any experience with medical jargon, or have maybe read any medical paper, or have done in school maybe something higher biology, you'll recognize this sensitivity and specificity, because that's what you want to get in drug trials, for example. So you want to have a high sensitivity, and you want to have a high sensitivity, you want to be right, and you want to be high specificity. Okay. That's what I just said. And the ideal observer would always choose the highest number of false alarms, the highest number of hits for the lowest number of false alarms possible. Interestingly, I got that from Wikipedia. This ROC curve, the receiver operating characteristics, is a strange word. Comes from America. They were used during World War II for the analysis of radar signals before it was employed in signal detection theory. Following the attack on Pearl Harbor in 1941, the United States Army began new research to increase the prediction of correctly detected Japanese aircraft from their radar signals. This is what a standard, a usual situation is. A radar operator sits in a room and gets some noisy input and has to say, yes, there is an airplane, or no, there isn't. Has exactly that situation. This is a color-coded version of the ROC curve that I just said. This is no aircraft, this is aircraft, and this is some internal decision criteria of the radar operator. And depending on where they are, and if it is a Japanese airplane, you can imagine that you want to be very careful. So you want to be with your criteria over there. Well, I don't know if you want to. You want to be in the middle, but some people are rather careful and want to be really sure that it is an aircraft. They would be over here. And some people are very anxious and say, yeah, everything is an aircraft. They would be over there. And so in this ROC curve, receiver operating characteristics, depending on their criterion, they would go to a very low number of false alarms or a very high number of false alarms, depending on that. But what you want them to be is pretty much in the middle. Same is true for the surgeon in hospital looking at an X-ray, deciding if they want to operate or not. It's exactly the same issue. You've got a noisy picture, and you need to make a noisy decision based on the best evidence that you have, and your criterion, your personal criterion, decides if you are rather too cautious or rather too daring, but you want to be in the middle. Now, all of that last half hour, I talked about how you shouldn't do these experiments, but in fact it turns out that many, many, many situations in real life are exactly following that yes-no criteria, because you haven't got any other option. You either have to say yes or no. Yes, I do the surgery, no, I don't do the surgery. You haven't got, well, you've got other data maybe to go on, but the basic criterion is still you've got a noisy decision to make, and this is the problem with it. Now, after I said all that, we basically can say the experiment that we did last week is fundamentally flawed because of that reason, because we don't know what the actual criteria is. We would like to know that our person would be here, but we don't really have any way of telling. Now, the next 10 minutes, I'm going to tell you how we do experiments that don't have this criterion, and are therefore criterion-free. And they're called two alternative forced choice. And you can listen to that, but don't worry. If I could play it to you, I would now play two intervals. That's why I always said two intervals. And your decision is not yes or no, I hear the sound or I don't hear the sound, but your decision is the sound was in the first interval or in the second interval. And what I present to you are two intervals, both with the same noise, but only one has the signal. Okay, now you can't have a criterion anymore, because the only way that you can make a decision is you're either guessing or you're hearing it, and then you make your decision on whatever internally happens in you, but you'll make it on the decision on if there is a signal in there or not, and not how sure you are that it is there, because you're forced to say either yes, or either the first one or the second one. That's why it's called forced choice, because I force you to actually take a choice between the two alternatives. Okay, that's an improvement of this no, yes-no paradigm, because we've got two sounds, two intervals, one has signal, one not. It has no criterion. This is an experiment that is criterion-free, works in all cases. People also can't cheat. They can cheat, they can lie, basically, if they want to, but they cannot just say, I'm cautious or I'm very daring. The disadvantage is I have to play twice as many sounds as before, and therefore it takes longer. And that's why it's only used in research, probably, but it's much, much superior. The thing is called two alternative forced choice. I always say 2AFC, or that's what if you Google it, 2AFC gives you the results. Chance level of that still is 50%. If you just guess, you get it right in 50% of the cases. Even better, it has turned out as a two alternative forced choice. It's a multiple forced choice experiment. That's an attempt to eliminate the influence of the degree of caution. What I just said, the two alternative forced choice with a chance level of 50%. Even better is a three alternative forced choice, chance level of 33% correct. The problem is, I said that first of all, it takes 3 times as long, so it gets worse, or you get a penalty in terms of how long experiments take, but you get a benefit of the more alternatives you have, the surer you are about your results. Yes, alternative may present different intervals, subject choose intervals. Yes, 3 alternative forced choices, noise, 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 but one of these intervals has the sound. So noise, noise plus sound, noise. And you must say which of these is the one that has the sound. Okay, this is what we're going to do in the practical. So listen closely. This is also explained in writing, but I explain it to you here what we're doing. All of these 2 alternative forced choice, or 3 alternative forced choice, or whatever you do, they usually come with a staircase method for practical reasons. And what we do is, as a function of time, these are the steps. We start up here. We start with a sound. Let's say we measure the sound, the amplitude of the sound to noise as before. So how loud has the sound to be, so that we can hear it. And we start with a sound which is very loud, so everybody can hear it. Okay? That's what I call the difference. Let's say 6% in amplitude, and you would hear it easily. Then you go, the rule is, you go down. Every time the subject says, yes, I hear it, or not yes, I hear it. When they take the right decision, they say, the sound was in that interval. And then you maybe turn the interval around and make the difference a little bit smaller. But because it's quite easy to hear, that you still pick the right interval, and that means you go down again, and you go down again, and you do that up to the point where you have to guess. And once you start guessing, at some point you just get it wrong, just by chance. This would be, in this case here, maybe at 3%, you would get it wrong. Then you go up, and you go to a slightly bigger percentage, which you already knew. Up here, you got it correct. But let's try it again. So you do that. But the trick is, and this is what it's called 2 down, 1 up, you need to get it right twice before you go down. Let's just assume that for a second that's correct. You get it right twice, you go down. You get it right twice at 3%, you go down. You get it right once, and then you get it wrong, and then you go up again. So every time you get it wrong, you go up. Every time you get it right twice, you go down. That's what's called 2 down, 1 up. But in fact, we only use the 2 down, 1 up from here onwards, because at the beginning we want to start very easy, and we go down in steps of 1. Okay, this is quite an efficient way of measuring a threshold. Why is that? First of all, it's better than a 1 up, 1 down. That's the standard way that you would think immediately. If you get it wrong, you go up. If you get it right, you go down. You don't want to do that for a number of reasons, because if you just guess, you would just disappear into randomness. If you just guess here, you would constantly go up and up and up over time. That's very useful, because you, by default, you go up to an easier condition, up to a point where everybody hears it. Secondly, if you do the calculation, the probability, if you just do the probability of how much you get them right, you come up with that the threshold is exactly at a specific DPrime value. And that's very useful to know. And thirdly, and probably most importantly, because of that, you will always operate in an area where it's quite difficult, where you're just about threshold. If you're below threshold, you don't hear it, you go up. If you're above threshold, you go down. So you don't spend time working up here with very easy signals, but you spend all the time working with the signals with the actual threshold. Yes, and the fourth reason why it is efficient is because it shifts the observer to be automatically in the optimum decision part of our ROC curve. So they will always work optimally here. They haven't got a choice, they have to. Okay. Last concept before the break is the equilibrium level. The equilibrium percent correct is the point where the subject has a 50-50% chance of getting it right. That's not the same as saying that you have a 50-50 chance to in a 1 up, 1 down, you have a 50-50 chance. You can say 2 intervals, you just guess which one it is. But this equilibrium point is where you actually have a chance of 50% observed to be right or wrong. This is slightly higher. And in our simple yes-no, so 1 alternative forced choice, I give you 1 signal and you say yes or no. It's a 1 alternative forced choice. You have a 50% correct chance. If the 2 alternative forced choice, you have it at 70%, which is very close to the threshold at the beginning of 75%. And that's why it's a useful threshold, which is quite often used. 70.1% is exactly what the result of the 2 alternative forced choices. So that means the subject, as at 70%, will have a half chance of getting it right or wrong. And that's easy enough to be an actual satisfactory experiment, and you don't have to guess. And this is the last table that gives for your reading pleasure what happens if you do 1 up, 1 down, 1 up, 2 down, 1 up, 3 down. So you can extend that, of course, where your equilibrium point is. So this is 50% in the yes-no. This is the same as saying the yes-no paradigm. You've got a 50% equilibrium point. And if you do a 2 alternative forced choice with that, you have a DPrime of 0, which is ridiculous. You don't want to do that, of course. But what you want to do is to have a 1 up, 2 down, and combine it with a 2 alternative forced choice, which gives you a level of D'Prime of the threshold, which is 0.7, and that's close enough to 1, not by definition, by convention, to say that's a reasonable threshold. Okay, and this is where I leave it with. You could choose to use others, and other people have done. In fact, some paper that I just read claimed that this D'Prime is the actual most efficient way to do an experiment, but probably not the fastest way. But anyway, this D'Prime here now is the final answer to the whole signal detection business that I'm talking about. I have told you and have made a case for that every decision that you take is subjectively influenced. There is a lot of noise outside and inside of your head that you can't get around, and we need a way to get rid of all of this noise and to get objective criteria. For that we need a threshold, and we need to define threshold, what we actually mean with that. And a very elegant definition of threshold is if we say we actually don't really care about threshold, we care about a D'Prime value, which tells us mathematically what the probability is that the subject has a 50% chance of hearing it, and this is at 70% equilibrium point for that criteria, for that method, for a 2 alternative forced choice with the 1 up, 2 down. That's it. What I want you to do is to actually run this experiment yourself. So you measure your frequency difference, Lyman, at 500 Hz and 8,000 Hz. Okay, let me just talk very briefly about what that is. I just use that as the... we actually talk about frequency discrimination later on, but it is straightforward to do the experiment. If you talk about threshold, we can talk about any threshold. I was always implicitly talking about the threshold of hearing in terms of amplitude, but you can make a case for a threshold in terms of how much do you have to change the frequency of the signal to be able to detect it. Equally important, and that's what we measure here. I just do that. We could do it with amplitude as well, but the results are less easy. So with frequency, it's fairly straightforward, and we do it at 500 Hz and at 8,000 Hz. For the simple reason that I expect that the literature that you're much better at 5,000 Hz than at 500 than at 8,000 Hz. So you get 2 different values. So you can generate the sounds or use sounds from Blackboard. They're there. And what the sounds are is they give you need a partner for that. They give you all the options of the differences in percent. So let's say 500 Hz plus 10% versus 500 Hz. And there are 2 options, namely the one where you have first the 500 Hz and then 550, or first 550 and then 500. So you need 2 people. One person knows what they're playing and the other one doesn't know. And the test subject needs to say which one is the higher sound. And if they're either right or wrong, and depending on that, I want you to follow exactly this 2 alternative forced choice, 2 down, 1 up procedure, according to this worksheet. And that gives you a threshold level that is your just detectable difference for frequencies. Criterion free. So that's a quite cool experiment. It should only take about 5 minutes. Well, if you know what you're doing. And I want you to describe that and understand that. That was it. Thank you. Have a break, and somebody help me getting these to everyone.